welcome to the deep dive. You, our listener, pointed us towards some really interesting research today.
Yes, definitely interesting.
We're going to be diving into natural radioactivity and heavy metal contamination found in common seafood, stuff people actually eat.
Right, from the Bay of Bengal, specifically the Kuakata region in Bangladesh.
Exactly. And think of this as, your shortcut, your way to get a quick but solid understanding of what this study actually found.
Yeah, the key findings, any health stuff, but without maybe all the super technical jargon.
We want you to feel informed fast. So the source itself, it's a scientific paper, right?
It is a research article detailing actual measurements they took. Natural radioactivity, heavy metals.
And they looked at quite a range of things.
Oh, yeah. Various fish, shellfish, molluscs, even seaweed, all collected right there in the Kuakata area.
Okay. And just to set the scene a bit, the Bay of Bengal is, it's a massive source of food for people in Bangladesh. So this is important stuff.
Absolutely vital. Okay, so where should we start? Radioactivity.
Let's do it. Natural radioactivity first. What exactly were they measuring?
They were looking for three main naturally occurring elements. You've got uranium-238, thorium-232, and potassium-40. These are things found naturally in, rocks, soil, water.
Okay, natural background stuff. And what did they find? The average levels in the seafood. Give us the numbers.
Okay, so the averages were 19.7 becquerels per kilogram. That's BQ/kg for uranium-238, then 12.2 BQ/kg for thorium-232, and 188 BQ/kg for potassium-40.
Right. And how do those numbers stack up? Are they high, low?
Well, here's the kind of headline news straight off the bat. Yeah. These average levels are actually below the accepted world average values.
Below. Okay, that sounds good. Significantly below. What are the world averages for comparison?
Yeah, it's helpful to see them side by side. The world averages are roughly 33 BQ/kg for uranium-238.
Okay, so 19.7 versus 33. Lower.
Right. Then 45 BQ/kg for thorium-232.
So I found 12.2. Much lower there.
Yes. And for potassium-40, the world average is about 420 BQ/kg.
Versus 188 in the samples. So across the board, the averages are lower than the global figures.
That's the picture, yes. Generally lower levels in these Kuakata samples.
Okay, so that's definitely reassuring overall, but I think I saw something in the study about uranium levels often being higher than thorium in the samples. Why would that be?
Ah, yes, that's a really interesting point. And the study explains the chemistry behind it. It's about how they behave in seawater.
Okay.
See, thorium isn't very soluble. It tends to sort of fall out of solution or stick onto particles.
Precipitate out.
Exactly. But uranium, it forms these soluble complexes with carbonate ions, which are, abundant in seawater.
So the uranium stays dissolved more easily.
Precisely. Which means it's more readily available for marine life to absorb or take up.
Ah, okay. So it's more about availability than just the raw amount present. That makes sense. Now, did the levels vary much between different types of seafood?
They did, yes. They found some clear variations. Generally, shellfish tended to show the highest levels of uranium-238 on average.
Shellfish, okay. Like crabs, shrimp.
Yeah, things like that. And interestingly, seaweed had the highest levels of both thorium-232 and potassium-40.
Seaweed, huh? Any specific examples that stood out?
Well, they mentioned mud crab had the highest uranium-238 of all the samples tested. And a fish called koi coral, sometimes known as black pomfret, that one had higher potassium-40 levels.
Shellfish and seaweed showing higher concentrations. I guess that ties into bioaccumulation, doesn't it?
Absolutely. That's a key factor.
Like filter feeders, the shellfish, are constantly processing water, right? And things higher up the food chain eat smaller things that have already picked up these elements.
Exactly that. Shellfish filter huge amounts of water, concentrating whatever's in it, and larger fish accumulate it from their diet. It builds up.
Right. The study also talked about gross alpha and gross beta activity. What are those measuring? Are they different?
Yeah, think of those as like initial screening tests. They give a general idea of the total amount of alpha and beta radiation coming from all the radioactive elements combined in the sample.
Before you look at uranium or thorium specifically.
Exactly. Kind of a first pass.
Yeah.
The average gross alpha was 9.4 BQ/kg and gross beta was 26 BQ/k.
And the beta was higher than the alpha.
Yes, and the researchers suggested that's likely just because there are more beta-emitting radionuclides present overall in the samples.
Okay, got it. General indicators. So the really crucial question then, what does all this mean for health? If you eat this seafood, did they calculate the dose people might get?
They did. That's the annual effective dose, or AED. It estimates the radiation dose someone would get per year from eating this seafood.
And the result?
The average AED they calculated was 216 microsieverts per year. That's easy CFE.
216. And how does that compare to safety limits?
Well, the internationally recommended limit is 2,400 microsieverts per year. So 216 is, considerably lower than that limit.
Okay, that's a big difference. Well below the limit.
Definitely. And they also noted that uranium-238 was the main contributor to that dose, even though the total dose is low.
Right. And they took it a step further, didn't they? Looked at cancer risk.
Yes, the excess lifetime cancer risk, or ELCR. It's basically an estimate of the extra chance of developing cancer over a lifetime because of this specific radiation exposure.
And what did that find?
That calculation also came out low. It was below the generally accepted permissible threshold, which is often cited as 10 other or 1 in 1,000.
Below that risk level.
Yes. And again, uranium-238 was the biggest contributor to that calculated risk, but the overall risk itself remained low according to their assessment.
So the bottom line on radioactivity seems to be, yes, these natural elements are there, but the levels found in this study and the resulting estimated doses and risks are well within international safety guidelines.
That's a fair summary based on this data, yes. Seems okay from a radioactivity perspective.
Okay, good. Let's switch gears then. What about the other side of the study, the heavy metals?
Right. They also analyzed for several heavy metals. There was iron, zinc, manganese, which we need in small amounts, and then the ones people worry more about: lead, cadmium, chromium, and mercury, the carcinogenic ones.
Let's start with those worrying ones then. Lead, cadmium, chromium, mercury. What were the findings there?
Well, this is another piece of quite reassuring news from the study.
Okay.
They reported that the levels of all 4 of those, lead, cadmium, chromium, and mercury, were actually below the detection limits of their instruments.
Below detection limits. So basically they couldn't find any measurable amount.
Essentially, yes.
Okay.
If they were present at levels that would typically cause concern, the equipment should have detected them. The limits were pretty low, too.
What were the limits, just for context?
Let me see. 0.21 milligrams per kilogram for lead and chromium, 0.18 millikilogram for cadmium, and even lower for mercury, just 0.08 micrograms per kilogram.
Tiny amount. So the fact they didn't detect them is definitely good news. Those really harmful metals weren't showing up.
Correct. Not in significant amounts based on these tests.
Excellent. Okay, what about the others then? Iron, zinc, manganese. We need them, but too much can be bad too.
Right. So the average concentrations they found were 42.01 millikilograms for iron, 52.4 millikilograms for zinc, and 22 low millikilogram for manganese.
And how do those compare? Are there recommended limits for those two?
Yes, the study compared them to the FAO/WHO recommended values. And this is where it gets a bit more, let's say, nuanced.
Ah, okay. Were some samples above the recommended limits?
Yes, there were quite a few instances, actually. For iron, the limit's 50 kilograms. The fish, koi coral, hilsa shad, and tuna were over that. And also shellfish, katacancra, the mud crab.
Okay, several over the iron limit. What about zinc?
Zinc limit is 40 kilograms. Even more samples exceeded that one. Koi coral again, kalachata, another pomfret, tin photocancra, a crab, chingri shrimp, katacancra, and even gray octopus.
Wow, quite a list for zinc. And manganese.
Manganese limit is much lower, 8 kilograms, and again, several were over. Koi coral, kalachata, rupchata, silver pomfret, tin photocancra, chingri, and katacancra.
So quite a few specific fish and shellfish samples had levels of iron, zinc, or manganese that were higher than those FAO/WHO guidelines. That sounds a bit concerning at first glance.
It does raise a flag, yes. But it's important to look at the whole picture they presented. Well, first, remember that seaweed sample, Eulothrix flacca? It had incredibly high levels. Iron was over 15,000 kilograms, and manganese was 555 kilograms.
Whoa. Those are massive numbers compared to the fish.
Exactly. It really shows how seaweed can soak up metals from the environment. It acts as a strong bioindicator.
Right. But back to the fish and shellfish people eat more regularly. Even with those spikes above the guidelines, what did the overall health risk assessment show for the metal?
This is the crucial part. They didn't just stop at the concentrations. They calculated the estimated daily intake, the EDI.
How much you likely eat per day.
Right. And they found the EDI for each individual metal was below the limit set by the WHO.
Okay, so even if a fish had high zinc, the amount you'd likely consume daily doesn't push you over the safety threshold for zinc intake on its own.
That's the idea. But they also looked at the combined effect. They used metrics called the target hazard quotient, THQ, for each metal, and the hazard index, HI, for the combined metals.
Right. THQ and HI, what do those show?
The THQ assesses the non-carcinogenic risk from each individual metal. For every metal in every sample, the THQ was below 1.
And below 1 is generally considered safe, right?
Yes, a THQ below 1 suggests no significant risk from that specific metal in that food item. Then the hazard index, the HI, adds up all the THQs for the metals in a sample.
To get the overall potential risk from the mix of metals.
Exactly. And the key finding here was that the hazard index, the HI, was also below 1 for all the seafood samples they tested.
Ah, so even though some individual metal concentrations in some samples were above recommended guidelines,
The overall assessment, considering typical consumption and the combined effect of the metals they measured, suggested that eating these seafood types from this area regularly does not pose a significant non-carcinogenic health risk, according to this study's calculations.
that's a really important distinction. The context matters. The total risk assessment paints a less alarming picture than just looking at individual spikes.
Precisely. It's about the overall exposure and risk, not just one number in isolation.
Okay, so let's pull this all together then. What's the big picture significance of this research? Why was it valuable?
Well, it provides really important baseline data. It's a snapshot of the current levels of natural radioactivity and heavy metals in this specific important coastal area, Kuakata.
A starting point for comparison later on.
Exactly. This kind of baseline is essential for future monitoring, especially, with things like the Rupur nuclear power plant coming online and maybe other facilities in the future in Bangladesh.
So they can track if things change over time.
Yes. You need to know where you started to see if there are trends or impacts later. It's like a health checkup for the marine environment there.
Makes perfect sense. Did the study suggest what should happen next? More research?
They did. They recommended doing more studies, naturally, getting more samples, covering a wider area perhaps, and crucially, sampling across different seasons.
To see if levels change, maybe with monsoon rains or different temperatures.
Yeah, things like that. Seasonal variations could definitely occur, so that would give a more complete picture.
Okay, so let's summarize this for you, our listener, who brought us this study. We've dived in, and the key takeaways seem to be:
Well, on the radioactivity side, the natural levels found were generally low, below world averages, and the calculated health risks were well within safety limits.
right. And on the heavy metal side, while some specific fish and shellfish did exceed individual guidelines for iron, zinc, or manganese.
The really toxic ones like lead and mercury weren't detected. And importantly, the overall health risk assessment, considering combined exposure through eating this seafood, did not indicate a significant concern based on the metrics used in this study, THQ and HI being below 1.
So a nuanced picture, but overall perhaps less alarming than one might initially fear, especially regarding the risk assessment.
That seems to be what this particular study suggests. Yes, it's a valuable snapshot.
Definitely. And it highlights the need for ongoing monitoring, as you said. So here's a final thought for you to chew on. Given that some metal levels were elevated in certain species, even if the overall risk assessment is currently low, what does that make you wonder about the longer-term health of the Bay of Bengal ecosystem? Could these levels change, especially with more industry, more development in the region? It really underlines how interconnected everything is, doesn't it? Environmental health, pollution, food safety.
It absolutely does.
Yeah.
These are dynamic systems. What's true today might not be true in 10 or 20 years without careful management and continued study. It raises important questions for the future.
Indeed. Well, thank you for walking us through that, and a huge thank you to you, our listener, for sending this research our way. It was a fascinating deep dive.
It really was. Thanks for bringing it up.
We hope this gave you that clear, concise understanding you were looking for. Until next time, on The Deep Dive.